was 2 years ago, when I was a graduate student at Berkeley, that I first came to know of an article written by Bruno De Finetti and published in 1940, named Il problema dei pieni, the problem of full risk insurances. It was Mark Rubinstein, who was teaching 2 classes in the Master of Financial Engineering program I was attending at Berkeley at that time, who told me about the article and asked me to translate it. And this is how I got involved into this whole thing. So today, I will start by reading the communications made available to this conference by Professor Rubinstein and Professor Markowitz. I will start by reading Mark Rubinstein's article, which is an historical note on De Finetti and De Finetti's paper. And then I will go through some passages from the Markowitz article, and Markowitz significantly titled his article, De Finetti Scoops Markowitz. Both these articles, together with my translation of Il problema dei pieni, have been published by the Journal of Investment Management in the special issue of 2006. After briefly going through some other historical notes, I would then like to present the terms of the reinsurance problem, De Finetti's reinsurance problem, how it differs from Markowitz's portfolio selection problem, how then De Finetti went to solve the reinsurance problem for the case of uncorrelated risks, and then how he solved it for the case of correlated risks. This will then lead us to Markowitz's critique on what he called the De Finetti's last segment conjecture. In summary, Markowitz admits that De Finetti, with 14 years before him, solved the case of portfolio selection for the case of uncorrelated risks, but also pointed out that he did not fully solve the case with correlated risks. In explaining the De Finetti model, the De Finetti problem and solution to it, I will not use any analytical formula, but I will just use charts and the geometric view. So, Mark Rubinstein said, Bruno De Finetti is generally regarded as the finest Italian mathematician of the 20th century. He died at the age of 79 in 1985 after writing over 300 scholarly articles. Among economists, he is very well known for his contributions to the axiomatization of subjective probability. But, to the surprise of many, it has just recently come to light, or should I say to the attention of economists in the English-speaking world, that among De Finetti's papers, there is a treasure trove of results in economics and finance, written well before the work of the scholars which are traditionally credited with these ideas. For example, in 1952, anticipating Kenneth Arrow and John Pratt by over a decade, he formulated the notion of absolute risk aversion, used it in connection with risk premium for small bets, and discussed the special case of constant absolute risk aversion. He has also early work on martingales, optimal dividend policy, and Samuelson consumption loan model of interest rates. But perhaps most astounding is De Finetti's 1940 paper, anticipating much of the mean-variance portfolio theory later developed by Harry Markowitz in a series of 3 works, and Andrew Roy. With the advantage of insight, we can see that Markowitz's work sparked development of modern finance theory and practice. Yet, 12 years earlier, De Finetti had already quietly laid these foundations. De Finetti modeled portfolio variance as a sum of covariances, developed the concept of mean variance efficiency, justified this criteria based on the normality of returns, considered the implications of fat tails, discussed bounds on negative correlation coefficients, and even worked out an early version of the critical line algorithm, the numerical method used to solve the portfolio selection problem. Given the prescience of De Finetti's work, how can it be that his contributions have hitherto been unknown among English-speaking economists, and in particular were not known by Markowitz until 2005? I learned about De Finetti's earlier work from Claudio Albanese, professor of mathematical finance at Imperial College London. When we first met at the Riskwaters Conference in London in 2004, when I gave a talk on the history of theory of investments. He felt that there was some history I did not know about, and he was right. Claudio, in turn, had learned of this from Francesco Corielli, professor of statistics at Bocconi University, who had learned many of the details concerning De Finetti's work from Flavio Pressacco, who knew De Finetti, now Dean of Economics at University of Udine. Indeed, Pressacco wrote a paper in 1986 in English that compares De Finetti's work to Markowitz, and in the same publication, the well-known financial economist Phelim Boyle also mentions that he learned of De Finetti work from Pressacco. De Finetti was probably motivated to write the paper from his brief time spent as an actuary at the Research Center of General Insurance. He then became absorbed by his other work in mathematics, and he may never have appreciated the importance of Markowitz's results. Invited by Linear Savage, he came to the United States in 1950 to attend a conference at Berkeley in support of his work on subjective probability. We speculate that, with the intellectual separation of academics in actuarial science and economics finance, and since his paper was only available in Italian, and a high-style Italian at that, those who knew of De Finetti's work did not communicate with financial economists, even in Italy. By the time Markowitz's work had appeared, De Finetti's was largely forgotten. Why did De Finetti himself, who spoke in English was good, and was certainly not shy, not bring this to the attention of those working in finance? Perhaps the key to this mystery is his daughter Fulvia's communication to Pressacco concerning her father, that as a general attitude of his character, he was not interested to claim merits for himself, but just to fight for the triumph of the ideas he thought to be right against the wrong paradigms. In view of the significance of De Finetti's contribution to mean-variance portfolio selection, and as a tribute to his predecessor, Markowitz has kindly provided a review of De Finetti's paper to accompany the publication of the English translation of its first chapter. Finally, we have Luca Barone, a recent graduate of the Master of Financial Engineering program at Berkeley, and now employed Goldman Sachs London office, to thank for the English translation, which has made all this possible. I would then like to go through a few passages from the Markowitz article, which is much longer than Rubinstein's review. And Markowitz says, "It has recently come to my attention that in the context of choosing optimum reinsurance levels, De Finetti in 1940 essentially proposed mean-variance portfolio analysis using correlated risks. About the same time, John Moore Williams, 1938, the leading financial theorist of the time, claimed that sufficient diversification can make portfolio risk negligible, implicitly assuming that securities returns are uncorrelated. Williams did not realize that when security returns are positive correlated, even unlimited diversification leaves a substantial level of portfolio risk. It was not until Roy and Markowitz that the notions of portfolio optimization with correlated risks entered the financial literature. De Finetti's analysis included what we now call the efficient frontier, which provides minimum risk for given expected return on the insured portfolio as a whole. De Finetti did not solve the problem of computing mean variance efficient reinsurance frontiers with correlated risks. It does solve it for the case with uncorrelated risks. For this case, he finds that the set of efficient reinsurance portfolios is a series of connected straight line segments and provides formulas for these successive segments. He explains why the reinsurance problem with correlated risks is more complicated and solves special cases of it. One of these special cases is that of small correlations, namely correlations small enough that the same sequence of efficient line segments occur with their exact position shifted a bit, as occur in the uncorrelated case. The other special case he solves makes restrictive assumptions on both the covariance matrix and expected returns. The De Finetti, Roy, and Markowitz models are special cases of a class of models for which a computing procedure called the critical line algorithm is provided in Markowitz 1956. While De Finetti does not solve the insurance problem with correlated risks, he outlines some of its properties. He tells where the efficient set starts, how it traces out a sequence of connected straight line segments, and then describes how it ends, i.e. the general location of the last segment of the path. I will refer to De Finetti's statement on the lateral matter as De Finetti's last segment conjecture. It is not correct. The De Finetti model does, however, admit of an interesting correct last segment proposition. Many properties of the solution to the Finetti model are already present when there are only two policies to be ensured. The next section of this paper defines the Finetti model, presents graph of all possible solutions to the two policy case, and sketches how the properties exhibited in these graphs generalize to the cases with any number of policies. It also shows which two policy solutions contradict De Finetti's last segment conjecture, and states the correct last segment proposition for the De Finetti model. The second section below solves a specific two-policy De Finetti problem and sketches how the principle illustrated in the example generalizes to the solution of problems for a number of policies. The computation of the two-policy efficient set in the example involves very little number crunching. It mostly illustrates how certain properties of the solution guide the critical line algorithm in tracing out the efficient frontier. The text is followed by the technical supplement whose three sections describe how to solve the De Finetti model for any number of policies, a proof of the correct last segment proposition for the De Finetti model, and some observations on developments in optimization techniques during the intervening years between De Finetti, 1940, and Markowitz, 1956. A translation of chapter number 1 of De Finetti by Luca Barone is presented later in this volume. Also in this volume is a historical note by Mark Rubinstein on Bruno De Finetti himself and on De Finetti, 1940. To summarize the acknowledgements that Harry Markowitz gives to De Finetti, he admits that De Finetti worked on the mean-variance portfolio analysis using correlated risks. He admits that he solved the efficient frontier for the case with uncorrelated risks, and in doing that, he anticipated a special case of the Kuhn-Tucker theorem. The critique by Harry Markowitz is that the critical line's last segment does not necessarily lie inside the legitimate set. We will go through the details of this statement at the end. Some other points I would like to make on this article, which I found pretty interesting. Bruno De Finetti basically anticipates two classical steps in capital allocation. What he called the problem of relative full risk insurances, which is the problem of identifying the efficient frontier, and then the problem of absolute full risk insurances, which is the problem of finding the optimal portfolio. He defined and analyzed the variable T, which he called the safety degree, which corresponds to what economists now know as Sharpe ratio. And then a little bit outside of the context here, but I think it's worth it to mention, because it's an embryo of Nash equilibrium theory that is also mentioned in a passage from this paper, where De Finetti says, if we consider several insurers who offer reinsurance to one another, and every one of these behaves when determining the levels of full risk insurances in the optimal way suggested by our preceding results, that is, each one seeks the solution which is the most advantageous for his own ends, it cannot be taken for granted that they will actually succeed in reaching their aim. This statement is related, as a particular case, to my preceding considerations intended to disprove the fundamental principle of a liberal economy, according to which the free play of single egoism would produce a collective optimum. Therefore, we will now try to see whether addressing the problem simultaneously rather than unilaterally, and using the conclusions of such a study to formulate a mutual convention rather than many unilateral decisions, it is possible to establish a different criterion, which for all and everyone is more advantageous than the one we found before. So as we proceed in this presentation, I will not use any formula to explain De Finetti's approach to the problem and De Finetti's solutions, but just charts. And the analytical framework is reviewed in my paper, Bruno De Finetti in the case of the critical line plus segments. Very briefly, some other historical notes I would like to make. It's very hard to find references to this paper. An exception is given by a short notice in the Journal of the Institute of Actuaries in 1947. An important acknowledgement comes also from Hans Buhlmann, who knew De Finetti. And then De Finetti's contribution to portfolio theory has been pointed out by Pressacco in 1986. And he says, Pressacco says, the name of Harry Markowitz is famous all over the world for his mean-variance approach to the portfolio selection problem, a milestone in the analysis of relevant economic problems under uncertainty. It is perhaps surprising to find that more than 10 years earlier, Bruno De Finetti used the same approach to study a key problem in proportional insurance, the optimal retention problem. Getting into the details of the problem. So, the reinsurance problem that De Finetti has is very similar to Markowitz's portfolio selection problem, but is formally different. In both cases, the aim is to minimize portfolio variance, given a certain level of expected return on the portfolio, subject to some linear constraints. Markowitz needs to select efficient portfolios where he can, by investing, studies how to select efficient portfolios by investing a unit of capital. In De Finetti, the initial portfolio is given, and he has to revise its weights by selling, i.e. reinsuring, some of the securities, which are in the case insurance policies, in order to obtain efficient portfolios. Therefore, in both the models, the aim is to find the optimal weights of efficient portfolios. So Markowitz, in the Journal of Investment Management article, approves the De Finetti analysis for the no-correlation case, saying that for the case of uncorrelated risk, De Finetti solved the problem of computing the set of mean-variance efficient portfolios. However, the solution of the reinsurance problem, i.e. the reinsurance frontier, will not necessarily represent the set of all the efficient portfolios, since we do not know if the initial portfolio is efficient or not. By looking at an example that Markowitz gives in his article, very easy one, where he assumes two securities with rates of return equal to 1 for both of them and standard deviations equal to 1 and 2. He defines initially the space, which is the space of weights. On the axis we have security number 1 or policy number 1, and on the x2 is policy number 2. Then he defines the isomean lines, which are the logical points where the expected return on the portfolio is constant. Then he defines the isovariances, which are the logical points where the variance of the portfolio is constant. Then this dotted line is the pure critical line, we call it, and it's the line that connects all the tangency points between isovariances and isomean lines. He then defines the legitimate set, which is giving boundaries to the maximum exposure and maximum reinsurance level of each policy phase. And then finally, the red line, which is the critical line, which is the solution to the problem. Starting from here, the initial portfolio, we will start by reinsuring security number 2. Then when we meet the pure critical line, along this line up to the origin for the zero variance portfolio. Perhaps it's better using Excel in showing some other cases. So let's first define what it is. This is basically, Harry Markowitz says the Finetti problem is a special case of a class of problems solved by the critical line algorithm presented in Markowitz. So I used the code available in Markowitz and Todd 2000 to write this code, which is Visual Basic for Application code, which solves the Finetti's and Markowitz problem. Let's look at the input of the model. So first we have to specify the number of securities. We start from 2, especially in this case. And the number of constraints, 1. The vector of expected return of the security in the portfolio. The vector of lower bounds for portfolio weights. So we said that we cannot reinsure more than the initial exposure we have, so the lower bound has to be set to 0. And the vector of upper bounds for portfolio weights, which has to be set to 1, because we cannot take a larger exposure than the initial exposure of the portfolio. This is the Finetti's problem. The correlation matrix with some assumptions between the correlation among securities number 1 and security number 2. The covariance matrix with assumption on the variance of security number 1 and variance of security number 2. And then the sum of the portfolio weights must be not greater than the number of securities, which is the linear constraint. So the output. The output, first we have the corner portfolios ID number. This is the number of corner portfolios which are solution to the problem, and any linear combination of corner portfolios is also a solution to the problem. The portfolio expected return at each corner portfolio. The standard deviation of portfolio return at each corner portfolio. The lambda. Lambda, let me just say something here. The giant upon whose shoulder the Finetti's solution to the reinsurance problem rely on is a shy and modest Italian born in Turin named Giuseppe Luigi Lagrange, better known as Joseph Louis Lagrange, who at the age of 23 worked out the method of Lagrange multipliers, which is used here to solve the Finetti's problem. And then finally we have this function that relates the variance of the portfolio between adjacent corner portfolios as a function of the expected return. And finally, we have the portfolio weights, the optimal weights at the different corner portfolios, so the solution. So this is the initial picture the initial chart we showed before. Let's now see if we change the return on security on asset number 2, how will the slope of the isomean lines modify? So we see that as we increase the expected return on security number 2 up to a level where the ratio of expected return per unit of sigma is equal for both securities, we are in the case of what the Finetti called the degenerate solution, which is the solution where all the efficient portfolios lie on the pure critical line. So this is the initial portfolio, and the solution will start by reinsuring proportionally each of the two securities. If we increase even further the expected return on security number 2, the solution to the problem will start from here, the initial portfolio. We'll start by reinsuring security number 1, and then as we meet the pure critical line up to the origin for the zero variance portfolio. Now let's look the same thing on the isovariances, and let's see how the shape of these isovariances modify if we decrease the variance on security number 2. So as the variance of security number 2 approach 1, you can see that the ellipses are no longer ellipses but are circumferences, because two securities have the same variance. And again, we are in the case of the degenerate solution, but the two securities have the same characteristics in terms of expected return per unit of risk. So we increase even further, as we decrease even further the variance on security number 2, we can see that we are back to a solution where we start from the initial portfolio, we start by reinsuring security number 1, and then on the pure critical line up to the origin. So this is the solution in the space of weights. What generally textbooks show is the solution in the expected return standard deviation space. And it's easy to connect these two solutions. We can see the connection between the corner portfolios and the solution in the mu sigma space, the space of expected return and standard deviation. And we can see that the line that connects the different corner portfolios in this space are segments of hyperbolas. Now let's look at the three-dimensional space. We increase the portfolio by one security, and we're still in the uncorrelated asset case. So we start by defining the new legitimate set, which is not a square anymore, but it's a cube. Initial portfolio being defined here. Then we'll add the isomean planes in Bruno-de Finetti world, the logic of points with equal expected return form a system of parallel hyperplanes. He was already thinking in n-dimension space. Then the isovariances are now ellipsoids. Bruno De Finetti says the lot of points with equal sigma are ellipsoids, concentric, homothetic, centered at the origin, and having as principal axis x1, x2, and x3 in this case. If we now rotate around the axis number 1, we can see the projection of the pure critical line being the solution to this problem. And Bruno De Finetti says if we do not consider the constraint on the weights, then the solution of the analytical problem is given by the straight line passing through the origin, which is the locus of all tangencies between ellipsoids and hyperplanes. What remains important, in Bruno De Finetti's work, is to see what is the role played by the constraints. It would be easy to see that the solution is the same as before, but now it is necessary to set equal to 1 all the xi, which will be larger than 1. So the solution will start from here, will move on the edge of the cube, and then through the pure critical line up to the origin. So the chart allows us to see the path along which it is more convenient to proceed as we decrease the risk by increasing the reinsurance. We spin the chart first around the x1 axis, and then around the x2 axis, and then the x3 axis. We can see, let me say something personal now. When I first read the article, De Finetti's article, I found it really complicated. I'm not a mathematician, so it was hard for me to understand, because when you approach the problem, it doesn't work out formulas or analytical formulas, which I'm used to. Like when I studied portfolio selection for Markowitz, I studied all the analytical formulas and everything, but he approached the problem and he sees the solutions in n-dimensional space, so it's really hard to follow him. So I think that perhaps in the three-dimensional space, which I'm allowed to plot in Excel, might be the way that De Finetti pictured in his mind the solution to this problem. The legitimate set, the line traced, so the solution, the red line, is a broken line which links the unit point, 1, 1, to the origin, here, the zero case, the zero variance portfolio case. The last segment is the part of the straight line, Bruno De Finetti's work, inside the hypercube, while the other segments are the projections of parts of the same line on the faces with n-1, n-2, 3, 2 dimensions, and finally on the edge. So now it would be interesting to see the 4 assets case, which is in De Finetti's paper is not just adding an extra asset, but it's considering the 3 uncorrelated assets and their portfolio. This will help us to understand some charts that is shown in the paper, which is the safety degree chart. So let's look at the first example that De Finetti gives. Now we are again, this is also another way of plotting the solution to the efficient frontier, where on the x-axis, here we have the lambda, which is the Lagrange multiplier, and here we have what he calls the safety degree ratio, the mu over sigma, so the expected return over the standard deviation of the portfolio. So looking at this graph, you can read it from right to left, and as we reinsure the portfolio, the ratio of expected return over unit of sigma, which is something we want to maximize because it's the measure of our safety degree, will increase as we always increase the reinsurer, if we keep on further reinsuring the portfolio. So eventually what this analysis is based on is that, differently from what is generally we assume, is that the expected return on the portfolio, it's not the sum of the expected return on the securities that constitute the portfolio. So it can easily be seen that if we reinsure completely our portfolio, our risk goes to 0, but we sacrifice 3 in terms of expected return, which leaves us with 0.5. So just a numerical example to explain how we get to this line, which eventually will tend to infinity. Now let's look at the example, which is the typical example that also Markowitz does, which is that the portfolio expected return is just the sum of the expected return on the 3 securities. So as we proceed from right left, we see that initially reinsuring the portfolio will increase our safety degree, but then further reinsuring will not be of any benefit. Then we see the case with some assumptions on the variance, and the case that the expected return on the portfolio is actually lower than the expected return of the securities within the portfolio. So initially, by reinsuring the portfolio, we can achieve a higher safety degree, but then at a certain point, further reinsuring will be not beneficial. Then, changing the assumption on the covariance matrix, we can see that the initial portfolio, if we start reinsuring the initial portfolio, will always end up in a situation which is worse off compared to the initial situation. So my interpretation of this problem is that probably Finetti was thinking of having a portfolio bought at some market prices in the past, and if he now has to go and revise his weights, market prices have changed, so not necessarily the expected return on the portfolio is the same as the one that will cost him to actually reinsure it. Now this was a little bit of introduction. Now we can get to the correlated assets case, which is the most interesting part, which is because it's where the Markowitz critique comes along. So we can see that the chart is pretty much unchanged. The only thing is that the orientation of the isovariances now is no longer flat, but it's like negative orientation, which stands for positive correlation. We can check how changing the correlation, decreasing it, will actually change the slope, the orientation of the isovariances. So we're back to the zero correlation case. Again, we have no orientation. If we end up in negative correlation scenarios, assumptions, we have positive orientation of the ellipsoids, of the ellipses. Now, proceed. So the two correlated asset case, how many possible shapes of the critical line we can observe? So the first shape is the one we observe also for the uncorrelated asset case. Solution will start from the initial portfolio along one of the sides of the square, and then as we meet the pure critical line, up to the origin for the zero variance portfolio. So the last segment lies inside the square. And we will start again by reinsuring policy number 2, and then by proportional reinsuring policy number 1 and policy number 2. This is the degenerate case, the case where we can see that the expected return and the variance of the two securities is the same. The two securities are similar, so we'll start by reinsuring proportional both of the security. And then if we increase the variance of security number 1 versus security number 2, we'll start by reinsuring security number 1 and then through the pure critical. Now let's get at the most interesting cases, which is where Markowitz critique comes along. So we might have cases where for some inputs of expected return, same as before, we didn't change it, the covariance matrix and some correlation assumption, then we might have a solution where the pure critical line never actually lies inside the legitimate set. So the solution here, the last segment, lies on the square bottom's edge. And again, if we switch around variances on the square left edge. Then we can have like some other cases with correlation equal to -1. Perhaps we can look at this one, which is, let's say this one, which is the case of securities which have the same characteristics, perfect negative correlation. Basically, the solution is a point, because you see initially on a portfolio which has zero variance, because the risk of one security offset the other, and so it's never optimal to reinsure any part of the portfolio. So coming to the end, the case for three correlated assets. Now we'll use Finetti's word, because it now gets to the problem where Markowitz critique comes along. So Claudio says, it is not difficult to extend the treatment applied so far to such a case because we only have to take into consideration the cross terms in the expression for sigma, take into account correlation. The geometric interpretation given for the non-correlation case still holds. Bruno de Finetti, the line of optimal points of sigma for given expected return is a continuous broken line which links the starting point to the origin. It moves at first on an edge of the hypercube until we finally proceed on the last segment inside the hypercube along the straight line, which is the pure critical line. Pressacco 2005 shows a necessary and sufficient condition for the last segment to lie inside the legitimate set in 3 dimensions when the correlations are uniformly positive. If Pressacco's conditions is not satisfied, the last segment lies along one of the hypercube's faces. See it here. If we rotate around the axis number 3, we can see that the pure critical line is outside the legitimate set. Or the last segment might lies on the edge of the cube. We can see it by rotating. As in number 2, we see that the pure critical line is outside the legitimate set. In these cases, the Finetti statement, until we finally proceed on the last segment inside the hypercube along the straight line, seems to be not correct. But so, to summarize the positions, is De Finetti's last segment conjecture not correct? De Finetti says, the geometric interpretation given for the no-correlation case still holds, since the line of optimal points of sigma for given expected return is a continuous broken line which links the starting point to the origin. Harry Markowitz says he tells where the efficient set starts, how it traces out a sequence of connected straight line segments, and then describes how it ends, i.e. the general location of the last segment of the path. I will refer to the Finetti statement on the latter matter as De Finetti's last segment conjecture. It is not correct. This controversy is based on one statement, which is the following. Until we finally proceed on the last segment inside the hypercube along the straight line K1, K2, Kn. Just to make sure it's not just my English translation of it. In Italian it says, finché finalmente si percorrerà l'ultimo tratto all'interno dell'ipercubo lungo la retta K1, K2, Kn. Markowitz says, in the De Finetti model with correlated risks, unlike the case with uncorrelated for the last segment, to approach the zero portfolio along the edge of the square or along the face or edge of the cube or hypercube rather than through its interior. So, the question is, did De Finetti solve the reassurance problem for the case of correlated assets? This is a crucial question because Harry Markowitz, for his research, was awarded a Nobel Prize in 1990. And perhaps De Finetti discovered most of his further discoveries by Markowitz 12 years earlier. So Bruno De Finetti, for the case of correlation case, the determination of the levels of full risk insurances entails the laborious, top per se elementary problem of solving a system of linear equations. Harry Markowitz, De Finetti solved the problem of computing mean-variance efficient frontiers, assuming uncorrelated risks, while he understood and explained the importance of the case with correlated risks. He did not provide an algorithm for that. So, there is no doubt that De Finetti used the word all'interno, inside, and lungo, along the pure critical line. However, to be meticulous, if you want, we can start by saying that the verb inside surely rules out the points outside the hypercube, but it does not necessarily exclude the points on the edges of the hypercube. The adverb along does not rule out the possibility of the last segment touching the pure critical line at the origin, through which the pure critical line must always pass. This is pretty much a detailed-oriented analysis, so perhaps a more reasonable justification seems to be the following. The position of the last segment, although it's very important is of academic relevance, because the position of the last segment leads to the risk-free portfolio, is unlikely to be important from a practical standpoint. And in Bruno De Finetti's word, there is a statement that gives support to this interpretation. And he says, all these equalities would be satisfied only when all the contracts needed to be reinsured, a point that is out of question in practice. This made me think of a little passage from De Finetti that I read at the end of the commentary made available to this conference on La Mania del Rigore, if I'm not wrong. So even if we're interested in the last segment from a practical standpoint, the circumstances under which the De Finetti statement is not correct are relatively rare. So let's see if we can draw some conclusions. So Harry Markowitz acknowledged De Finetti's contribution to portfolio selection theory, and he significantly titles his article De Finetti's Kurs Markowitz. He also recognized that De Finetti solved the problem of computing mean-variance efficient reinsurance frontiers for the case of uncorrelated risks, and he also gives him credit for outlining some of the properties for the case of correlated risks. He also acknowledged the fact that De Finetti was able to work out some special cases of the Kuhn-Tucker theorem. Finally, he points out the fact that De Finetti did not benefit from the same environment from which Markowitz benefited, which was an environment where the existence of the Kuhn-Tucker theorem, the success of linear programming, encouraged a presumption that a neat quadratic programming algorithm existed if we persisted in seeking it. Mark Rubinstein says that even if he did not fully work out the critical line algorithm, Bruno De Finetti did actually lay, in 1940, the foundations of modern finance theory. So it is very surprising to me how this outstanding piece of research has remained unknown for so long. And I think that the help of historical economists would be very much appreciated in this case. We can conclude by saying that, we conclude with a question saying, after Arodebreu, Modigliani Miller, and Black and Scholes, has the time finally come to talk about De Finetti Markowitz portfolio selection theory?